Okay guys, so as we deal with the VBT, valence bond theory, we came to know with respect to the main postulates that through the help of the VBT, we are able to predict the geometry of the complex. That how does a central metal atom or the ion is providing the vacant orbitals. It also explains that how these vacant orbitals are undergoing hybridization, and with respect to the hybridization, how it is going to explain the geometry of the complex. We are going to see with respect to the VBT approach the geometry of the complexes. First and the foremost thing, let us take an example, very much important example of first one, CO NH3 3 plus. Yes, of course, if I go with the name, can you be able to name this? Very much easy. Totally there are 6 ammonia and it is a neutral ligand, and moreover it is a cationic complex. Alva? So how can I write it? Hexa amine. Yes. First I have named the ligand, next I have to name the central metal atom or the ion. Hexaamine cobalt. Because it is a cationic complex, the name of the central metal atom or the ion remains as it is. What is the oxidation state? Since our ammonia being a neutral ligand, so therefore X plus 6 of 0, overall complex charge is plus 3, so it is having the charge of, or the oxidation state of 3, which is written in the Roman numerals. Since it is an ion, so hexaamine cobalt third ion. But now with respect to the VBT approach, that is the valence bond theory, now we are going to say that what would be the geometry of this complex. So first and the foremost thing, we have to see that here the central metal atom or the ion is your cobalt. So when you're choosing your cobalt, we know that the atomic number of cobalt is how much? Iron, alva, scandium, titanium, vanadium, chromium, manganese, iron, cobalt. So it is 27. So when I write its electronic configuration, so when I'm writing its electronic configuration, how can I write? Argon configuration, true, which means it is having 18 electrons. Argon means 18. Then afterwards, argon 18, 19, 20, 3D 7. Alva. So this is with respect to the cobalt element. But when I am taking my complex, I have got that in the complex the cobalt is not existing. So in the complex, what is happening? Cobalt is in the plus 3 state. So your plus means what? That much electron has been lost. So what happens in that case? Electronic configuration becomes how much? 24. So when I am going to write, I will get the electronic configuration as argon 3D. Here 2 electrons is gone, here 1 electron is gone, 3D is 6, but I am going to write my 4 as 0. Let me take it. So now when I am writing in the box diagram, okay, let the box diagram with respect to the representation. So how can I write my box diagram? Of course, my d orbitals, I know there are totally 5 d orbitals. 1, 2, 3, 4, 5. Of course, for my consideration, I will take my s as it is. Let this be your 3D, this be your 4s. So here, in order by following your Hund's rule, by following the Hund's rule, we can just write the electrons in this way. First, individually in all the part 1 electrons, then afterwards 1 more electron. 3d6, 4s, 0. So this is a representation of your cobalt in the absence of the ligand. Till now the ligand doesn't approached. But now what happens when the ligands are coming? Since your ammonia being a strong ligand, the pairing of the electrons takes place against your Hund's rule. That is, how can you write? Means, so here my ammonia is a strong ligand. So it being a strong ligand, the pairing is taking place against Hund's rule. Against Hund's rule. So what happens now if I'm going to write, you just see that first you write 1 2 3 4. So here however 2 electrons, so now this electron will jump over here. Okay, now this will be vacant, so this electron will jump, this electron will be jump. So you will be having the vacant now D2s, and also please remember the coordination number of the cobalt is 6. So according to your VBT, what does it says? The central metal atom or the ion produces the vacant orbitals equal to its coordination number. So it will be also having your p orbital, which will be vacant, of course. So what happens, it needs how many? Totally 6 ammonia molecules, so 6 vacant orbitals it would require. So 1 2 3 4 5 6. So now this part will are called as a vacant orbitals. Of course you could just see that this is D, this was S, this is P. Now they will undergo hybridization to give you the hybridization of D sp2 2 3 sorry D2 sp3 D2 sp3. Able to understand? So now when it takes place with respect to D2 sp3 hybridization, you should write it in this way. Of course the one which is present with the electrons, the orbitals will remain as such, they are not involved in the hybridization. Only the vacant orbitals are involved. Totally how many vacant orbitals? 6. So 1 2 3 4 6. 1 2 3 4 5 6. So this is your D2 sp3 hybridization. Yes. Yes. So it is now becoming your D2 sp3 hybridization. Now these vacant orbitals, what it will do, it will overlap, or it is going to accept the electrons which is being donated by your 6 ammonia ligands in order to form the overall complex electronic configuration in this way. So all these electron or vacant orbitals will be filled . So these vacant orbitals are filled by the electrons donated by your 6 ammonia molecule. So in this structure we could see that all the orbitals are filled and no other electrons are present as an unpaired. So whenever all the electrons are filled, we will be saying its magnetic property as what? Diamagnetic. That is, they are strongly repelled by the magnets. Coming with respect to the geometry part, remember. So in the geometry part, what type of a hybridization it is undergoing? D2sp3. So of course it is having a geometry of octahedral. Magnetic, and also we came to know the hybridization. Initially we have come to know, but in the final step in your exam also you have to write it at the last. It is having a hybridization of D2sp3. Now the question arises as, how does this molecule look? So basically if I write its geometry, of course the molecule looks in this way in a general course as NH3, 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 NH3. Remember it is an ion, so this should be written as 3+. While writing the structure you should make an aware that, see here our nitrogen is our donor atom. So whatever the bonding representation is there, that should be attached with respect to your nitrogen itself, not the hydrogen part. And they are all having the directional properties because they are donating the electrons to your central metal atom or the ion. So this will be the structure of your, what you can say, cobalt, hexamine cobalt third ion. Is that clear? One more important thing I have to mention over here is that, so basically whatever I have written, of course you can just see that this is your octahedral geometry. Alva, this is your octahedral geometry. This is in a 2 plane, but in the 3D representation, of course it's not needed. for your classes, but have a knowledge of it. When you are seeing, see the octahedral geometry, you could see that there are three types of your bond representation. That is, one is written in this way, okay, and one is written in this way. The second one is written in somewhat shaded part, if you could notice, like this shaded part, and the third one is your dashed lines. So whenever you're writing a molecule, guys, remember, so whatever we have written over here is just a mere representation. But when you're seeing a three-dimensional figure, it will be, the bond representation will be shown in this way. This means what? The lines which is represented in this way, a straight line, it means they are in plane. If I am writing in a blackboard, means of course it is in that plane. This some shaded line, which means that it is, the bond is towards the observer, that is, it has plunked out. For example, if this is your plane, if I consider this sheet as a plane, the bonds which is written within this page will be acting as what? This line. If the same book, if like this a bond is coming out of this book, that is represented by this shaded line, which means what? Towards observer. That is, you're observing and the bond is coming towards you. The dashed line means what? The backside of the book. If I'm writing this one as a plane, whatever is going backside of this book, that is called what? Away from observer. Away from observer. So if I write the same structure in the three-dimensional figure, I could write it in this way: NH3, 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 and this way you will be getting your figure or the geometry, where the two ammonia molecules are in the plane, two are towards the observer and two are away from the observer. So this is called as your stereochemistry, which is very much important in your higher classes or in our organic chemistry. But for a while you just remember to write in this way. All the bonds will be written within the plane itself, but when you are writing the bond, you should be very much careful that the donor atom should be bounded with respect to the bond, not the other any atoms. One which is donating the ligand, that should only be represented with respect to your arrow marks. Is that clear? So this was the case with respect to your CONH3 6,3+. Now the next example we are going to choose is called as that of your COF6 3-, COF6 3-. Let's go with it now. Okay, of course, the first important thing, let us go with the cobalt atomic number. What is the atomic number of the cobalt? We know that is 27. So electronic configuration of an element will be argon 3d 4s2 18 19 20 3d 7. But in the complex, what is the oxidation state? Of course, X I am writing. There are fluorine over here. Since ammonia was a neutral ligand, I took it as a 0. Here fluoride means what? It is an anionic ligand with a charge of -1. So X plus of -1. One fluorine charge is -1. How many such fluorines are present? 6. So -1 into 6 overall is equals to -3. So X is equals to -3 plus 6, that is equals to +3. So cobalt +3 means it will be having the argon 3d6 4s0 and that of your 4p0. Okay, so now, since when you are writing with respect to the box diagram, you can easily write it. Box diagram, how you are going to write it? Let me write. So this is your d orbital, 1 2 3 4 5. So 4s is also empty, 4p is also empty. Yeah, so when you're writing over here 1 2 3 4 5 6 with respect to your Hund's rule. Now you have to remember over here that fluoride, whichever you are taking, fluorine, the ligand, It is acting as what? Weak ligand. It is acting as that of your weak ligand. There our ammonia was acting as a strong ligand, whereas our your fluorine is acting as a weak ligand. So whenever the weak ligand comes into existence, this doesn't have that much force in order to pair the electrons against Hund's rule. So what it will try to do, it will only try to take the orbitals which is at the outer part. That is what is happening means. However, we know that now cobalt has to provide 6 vacant orbitals. Of course, the vacant orbitals here, since they are having the electrons, we can't call them as a vacant orbitals. And since fluorine being a weak ligand, it cannot pair these electrons against Hughes rule. So it is going to take the electrons, or take the orbitals away from it. How many orbitals it would require? 6 orbitals. So what it will try to do, so fluorine being a weak ligand, this d orbital, inner d orbital will remain as such. 2, 3, 4, 5, 6. Of course, now S it will be taking, P3 it will be taking, and the outward part may you are having. So this is your what? This is your 3D. This is your 4S. This was your 4P. Here also now your 3D. Here is your 4S. Here is your 4P. This is your 4D. Since now it has to take the vacant orbitals, now it is choosing 1S, 3P and 2D. So undergoing a hybridization of sp3d2. sp3d2. Okay, so now these sp3d2 hybridization takes place, that is these vacant hybrid orbitals. So the vacant orbitals undergoes now sp3d2 hybridization to form an sp3d2 hybrid vacant orbitals. That is what is happening means you will be having as such 3D. Yes, and now totally 6 orbitals it will be remain vacant. 6. So now this will be called as what? sp3d2 hybrid vacant orbitals. Utilizing now cobalt will utilize these sp3d2 hybrid orbitals to accept the electrons donated by your 6 fluorine atoms, giving you the overall configuration. After your complex has been formed, the complex formation will be in this way. That is, and here what happens, all the vacant orbitals will be having electrons donated by your ligands. But here we could just see the difference with respect to the first example and the second example, the magnetic property. Since here electrons are not paired up, so it is paramagnetic. That is, they are attracted towards the magnetic field. Coming with respect to the hybridization, we came to know that it is sp3d2 hybridization. Coming with respect to the geometry, of course it is also having your octahedral geometry. So when you're writing it, of course, how you're going to write it? CO, fluorine is our part, which is donor over here. It's a unidentate ligand, single donor atom. It is an ion, so it is having 3 minus. Can be the name? Can anybody say its name? Yeah. So first and the foremost thing, it is an anionic complex. So the central metal atom or the ion name ends with 8. So the name of the complex is, how you will write it? Hexa, yes, fluorido, alva, because it is an anionic ligand. Hexafluorido, and it is an anionic complex because an anion is present. So I will be having cobaltate, 3 ion, hexafluorido, cobalt 3rd ion. Is that clear? But now with respect to both the examples, I want to just define what do you mean by inner orbital and outer orbital complexes. So basically in CONH3 3+, you could just notice that here in the hybridization it has taken 3D, 4S and 4P. In simple words, it has been taken, if I consider as N is equals to 4, it has chosen n minus 1d orbital, that is inside d orbital, 3d orbital. 4 as the n value, but it has taken a n minus 1 3d inner d orbital. So this type of a complex will be called as what? Inner orbital complexes. So CONS363 plus is an example of your inner orbital complexes. But when you are choosing for over here COF63 minus, we could just notice that here whatever the value of n was there, that is n is equals to 4, the same value n value it has taken for your 4d orbital, that is it has been chosen your d orbital which is having the value of n is equals to 4. That is the reason it was having sp3d2. So this is an example of your outer orbital complex. Why it is called as an outer orbital complex? Because it is using the orbital, it is using the d orbital which is outside. Okay, nd, that is it is using nd, ns and np. Whereas in the CONS363 plus it was using n minus 1d and ns and np. Able to understand the difference? The same way it was also called as a high spin complex, that is your, what you can say as that of your outer orbital complex. Outer orbital complex is also called as your high spin complex. Can you anybody say why is it so? It is mainly because you could see that here they are not paired up. That is, these electrons are spinning. That is the reason they are called as a high spin complex. Whereas when you are coming with respect to your inner orbital complex, they are called as the low spin. Why they are called as low spin? If you could just see that here all the electrons are paired up. No electrons, that is if one electron is moving with plus half, having a spin of plus half, of course within that orbital itself is also having a minus half. So it is having a zero spin. So it is also called as a low spin complex. Inner orbital complex also called as a low spin complex, whereas that of your outer orbital complex is called as that of your high spin complex. Coming to the next example now over here, let us take NiCl4 2 minus as an example. Okay, till now we have seen with respect to the cobalt